like to welcome you to the final dissemination event of the research project Runway Micro Texture. Next slide, please. You have here a short disclaimer. I will not go through that, but just that you know that we have here content which has been worked out by a contractor. EASA has the intellectual property rights to that. And important to know also is that this research project received funding from the European Union Horizon Europe Research and Innovation Program. The European Commission has delegated the funds to EASA, and EASA has a portfolio of a number of research projects. And what we usually do is that we have a public tender procedure. This was also the case in this project, and we selected NLR, or a consortium which is led by NLR, in order to conduct this research project. This portfolio of around 30 research projects which you currently have, they are all dealing with aviation authority research needs, and this is an important pillar for EASA and for other aviation authorities in order to make sure that we upheld aviation safety. Now, let me please go quickly through the agenda. We will start that my colleague will give you a short overview about the research scope and the objectives. Then we will hand over to our contractor, NLR, who will provide an overview of the project implementation and, of course, the key results of this project. Then I will hand over again to my colleagues who will debrief you on the benefits of this project and what kind of follow-up actions are now planned. And then, colleagues, we come to you. We will have a question and answer session of around 1 hour, and we will then conclude around 5 p.m. For the questions and answers, we would like to use Slido. You see here the QR code. You can also do this on your mobile phone or on your desktop when you click in the slido.com address. You have here the event code and there's a bus code. In the meantime, colleagues, let me please introduce you here, the colleagues which are in the room. I start with Gerrit. Gerrit, he is from NLR. Gerrit van Ees acted as the project manager of this research project. We have here Peter van Geest. Peter was the technical lead. Then we have Vincent de Vries, who acted as key expert for the flight test campaign. Then here is Vasilis, who is a senior expert in the aerodrome section and was acting as the technical lead at EASA. We have here Julia, who is the section manager of the aerodrome section at EASA, who acted as the project owner. And last but not least, my colleague Giovanni Cima, who is a senior expert in the Air Ops section and also was very active in this research project. Yeah, and my name is Willi Siegel and I acted as the contact manager. With that, colleagues, I would like to hand over now to Vasilis in order to give us an overview about the research project and the scope and objectives.
Thank you very much, Willi, and good afternoon to everyone. So, when we decided to initiate that project, there were some good reasons behind this decision. And based on the data we have and the analysis we did, the runway excursion is one of the main key safety areas for commercial air transport, business aviation, and non-commercial operations with motor-powered aircraft. And what has been identified by looking into the different excursions was that water runways are contributing factors I will not say that they are the only ones, but they are contributing factors to runway excursion events. And on a runway surface, we have two features of the runway surface, macro texture and micro texture, which are very important to ensure good braking performance. And when we talk about macro texture, we refer to visible roughness of the pavement surface, while micro texture refers to the roughness of the individual stones that form the macro texture. Now, macro texture can be measured through simple methods which are well known. For example, the sand and grease patch method. For the aerodromes, they are very familiar with using continuous friction measurement equipment, which mainly assess the effect of macro texture. But for micro texture, there are neither minimum requirements nor an established method for determining and monitoring microtexture characteristics. So, what we want to achieve through this project, first of all, is to correlate the microtexture characteristics with the aircraft braking performance. We want to identify some threshold values below which a runway becomes slippery wet, and at the end of the day, to provide a practical guide which can be used by the aerodrome operators, the competent authorities, and the accident investigation bodies by use surface laser scanners to assess the runway microtexture. And saying that, I want to pass the floor to Gerard, which he will provide with the main results of the research project.
Thank you, Vasilis. Good morning, afternoon, evening, I'm not sure, night, I don't think so. To all of you, my name is Gerard Van Ness. As I really already told in the introduction, I was the project manager of this project. In my brief, I will discuss the typical topics that we dealt with within this project, some of the main results and findings, and the next steps that we foresee. Most of the material that we will present is described in detailed reports that will be available through the EASA project website that is related to this particular project. That gives a much more detailed overview of what we have been doing and the technical background of this. First of all, just a brief introduction on what we are talking about, and this is very brief indeed. It can take days if you want to discuss everything, but we still want to give some feeling on what we are talking about, and these are the basics of wheel braking in general. So if we are looking at wet runway braking forces that are generated between the tire and the surface, there are a number of factors that play an important role. First of all, that was already mentioned, is the runway texture, which separates in a macro and a micro type of texture. The speed of the aircraft, the forward speed, the tire pressure, but also the tire characteristics in terms of size can have a factor. The anti-skid, the anti-skid system, which is an important element in the overall control of the braking friction forces. When we're looking at wet runways, and this is all about wet runways, the amount of water there's on the runway surface. So the amount of water that is being between the tire and the runway surface. The loading, the normal load forces that are on the gears that will transfer into forces. And finally, also the surface temperature can play a role in all this generating of wheel braking forces. These are just a summary of a number of factors that you have to take into account, into consideration. So we already talked about micro and macro texture. Just to dive in a little bit deeper what we are talking about. So if we have a surface, being pictured like this, the macro texture is formed by the individual stones that you will find or have in this particular surface. And they can be characterized by an average size in terms of the height of this texture. The micro texture is actually the sharpness of the individual stones, and can also be the aggregate in between the stones that keeps everything together. And it's actually a sort of sandpaper roughness that you can feel. The same holds for a groove runway. So if you have a groove runway, there in between the grooves there can be still, and there needs to be still a micro texture, and it's not being replaced by the grooves themselves, which is sometimes being suggested. So in between the grooves of a groove runway, the micro texture there still plays an important role. Just a little bit further, this is a picture depicting the tire that is running from right to left on the screen over a wet surface, and underneath the tire, the classical way of looking at it is that we see a couple of zones that separate the tire from the surface. So we have a zone 1 and a zone 2, and both can be separated. This is the zone that is separated by a layer of water. Whereas zone 3, that's behind the contact area, is where you have dry contact with the tire and the surface. If we zoom in a little bit more on this, this zone 1 is where we have what we call dynamic hydroplaning. That's where the water is first contacted with the tire, and the inertia forces, form the size of it. Now, the size of this zone is very much dependent on the macro texture of the surface and the forward speed. And the zones tend to increase if you have lower macro texture or you have a higher speed. There are also other factors that play a role, but these are one of the important ones. Zone 2, where we also have a separation of the tire with water, there's a much thinner layer of water in existence there, and it's where we say viscous hydroplaning is acting. This viscous hydroplaning and this area is determined by the microtexture, and it becomes larger if the microtexture is smoother. So if you have a smooth microtexture, this zone will typically be large. It's not very dependent on speed, so it can be present at very low speeds. That's a difference where you have with zone 1, which is very much speed dependent. And finally, I said zone 3, that's where the dry contact is. It's where basically most of the friction, the actual friction, is generated. So a reduction of braking forces on a wet runway is characterized by this kind of mechanism. So now we get to what we call slippery wet runways. I always used in the past, but I'm not a native English speaking person, I use slippery when wet, which is also the title of a record or an album. But it's slippery wet runways. There are several definitions, and we took the definition that is most commonly used in the regulatory world. And it says that a slippery wet runway means a wet runway where the surface friction characteristics of a significant portion of the runway have been determined to be degraded. Now that sounds like, okay, you could have a problem, but it's not very clear what it actually means. It's still a bit very general what means slippery wet. So you have a wet runway and you have a slippery wet runway. That seems to be the case. So when we go to this is something that is very familiar now, which is related to the global reporting format that we currently are using and been using for the last many years. And it describes the runway surface by describing what is on it, and associated with each code is a level of braking that the aircraft can achieve. And when we look close to it, we see a wet runway being defined. That could be on a wet runway being with a smooth surface, not a smooth micro texture surface, but a smooth macro texture surface, or grooved or porous friction cores. And we have wet, slippery, which has a braking action medium. Which, if you look at the description, is the same as what you can expect on dry snow, wet snow, compacted snow at different temperatures. So that's the way the condition is being described. And behind this, there is a braking friction level associated that the aircraft tires can generate, which is then used also for making performance calculations. Here's an example of that. On a typical aircraft with typical characteristics. So what you see here is a picture, a plot showing the ground speed on the horizontal axis, and on the vertical axis you see the wheel braking friction coefficient, which is basically the ratio of the braking force over the normal wheel load. The solid line is what you will have with a runway condition code of 5 on a wet, smooth macro texture surface. The dashed line is what you would expect on a slippery wet runway. This is these are the values that are being assumed for performance calculations. Now, you can find the levels of braking friction for this runway condition code 5 in EASA CS 25109, but also in the FAR 25109 sections D and D. There's a dependency on the tire pressure and the anti-skid efficiency and the ground speed. But what is most importantly, that whatever there is defined, it assumes sharp microtexture surfaces. So there are relations within CS 25109 given, but they are based on empirical data that was gathered on sharp microtextured surfaces. So that's important to understand. The level of slippery wet, it's a constant coefficient, which only varies depending on the anti-skid type that you would select. And in this example, it's a fully modulating anti-skid. That's what you will find on most of the modern aircraft flying around nowadays. So where does this originate from? Partly from Talpa ARC, an initiative to better condition the runway conditions and related to braking performance. And they proposed that slippery wet would relate to a braking performance of medium. There we go. And the braking friction coefficient chosen for this particular level is 0.16 for a fully modulating anti-skid system and a 10 for what is called a quasi-modulating anti-skid system. And this number actually was derived from a number that is used and was defined by EASA and was lowered a little bit. So it was a value that was chosen from a working group without much attention to the full details of what is actually happening. And as I said, it's not only for wet runways, but it's also for snow and wet snow contaminated surfaces. So if you look at some examples, and what we did, we looked at particular at accidents in which the investigators found that the braking friction values were much lower than expected, and also some flight testing. We looked at what levels of braking friction were achieved. So the next plot shows, it's a bit busy with a lot of colors, shows the ground speed versus the wheel braking friction coefficient for a large number of different aircraft on wet, ungrooved runways. And the different colors are for the different aircraft that we had data for. We also see the lines for a runway condition code 5 for a smooth runway, assuming a 80% anti-skid efficiency for different tire pressures, but these are the ranges of tire pressures that you will find for these aircraft in the plot. It also depicts the runway condition code 3 braking friction coefficient for a fully modulating value. And what you can see is that at certain levels, and these are not flooded runways, these are just wet runways, we see very, very low braking friction values. Sometimes, lower than 0.05, which tends to go to values that you will find on an icy runway. Sometimes you see levels that match with the CS 25109. That particularly has to do with the location on the runway. Some of these cases, the runway along the runway, the surface condition changed a little bit. Some of them were refurbished, and some of them were older parts of the runway, and that's why you can see it sometimes changes. It has nothing to do with a change of the effect with the ground speed. It's just to do with the properties of the runway surface changing. We have the same graph here for grooved runways. Some people think grooved runways are exempted from this problem. That is unfortunately not true. So again, we have cases mainly derived from accident investigations, wet grooved runways, not flooded. And again, you sometimes see it matches with the CS 25109 values, but if you look closer from some of these lines, it drops below at certain parts, which is again attributed to the changes along the runway surface, where the runway texture varied along the runway in certain areas. And again, you see sometimes very low values, some of them reaching those that you will find on an ice-covered runway. So when you look at this, we can see that we sometimes see values of the braking friction coefficient that are 80% lower than assumed for a runway condition code of 5. And as I said, sometimes lower than what you will find on a snow or ice covered runway. The differences that we see, we think is mainly caused by variations in the texture along the given runway. So micro texture is dominant in here. It's typically smoother than assumed in where the standard curves in 25109 were based on, and viscous hydroplaning is a very dominant factor, we think, and that is sometimes that we see that the variation with ground speed is not there, not as much as you would expect. It's very stable, and that's typically something that you can trigger as viscous hydroplaning condition. You don't need a lot of rain or a very wet runway to get to these conditions. 0.5 millimeter of water on your runway surface in the areas where the main gear wheels are can be fully sufficient to get these low values. So the current way of assessment of when a runway is slippery wet it's based on mainly on the use of continuous friction measurement equipment, the CFMEs. And what we do is we run these devices along the runway through certain protocols, and we compare that based on the manufacturer and the type with a minimum friction level, which has been defined for that particular device. And as you are below that particular value, you can declare that the runway is slippery wet through a NOTAM that will reach the pilots. What we have seen, and there are many reasons for this, that CFMEs can give optimistic results. That is, they give higher friction levels than what is actually out there. And this is a topic on its own. There are many factors that can play a role in why this is the case. Some of the airports have the experience that they have two CFMEs which are of the same model type and manufacturer, and they simply cannot get the same results when doing successful runs with these devices. We also have to understand that the actual level, the minimum friction level, it was slightly arbitrarily chosen based on partly experience and also highly scattered data. So that's typically what you will see if you going back in history and see how these things were defined. And it goes back to the early 1970s. Another mean that you can do is observation by the aerodrome maintenance personnel that look at the runway, that feel the runway. You can identify in this way rubber deposits, but it's not always sufficient to identify that the runway could become slippery when it's raining. It's very subjective, basically. Then we have the pilot reports. Pilots can report that they feel that the braking action is not sufficient. But we know from experience that this can also be very subjective. For instance, thrust reversers, they can be very powerful and they can mask the true braking performance. Something very new is real-time onboard analysis of braking performance, which should give a much more objective understanding of the runway braking performance actions. It is really promising, but you do need a wet runway, for instance, first, and you need friction-limited braking to be able to assess the full braking performance potential. That will not be always the case. Even if you have a runway, it will not necessarily give you friction-limited braking, especially if you're using thrust reversers. And if you're an airport, as an aerodrome, you also need aircraft that are actually equipped with this mechanism, this system. If they don't come to your airport, or they don't come as regularly, you might not know that your runway is deficient in terms of when it becomes wet. So there are some challenges there. Here's an example that I will show of CFME results related in an accident investigation involving a Boeing 737 overrun. What you see here is the braking friction coefficient. In this case, the CFME measured braking friction coefficient at 40 miles per hour along the runway, and the distance that you show on the horizontal axis is taken from the runway threshold. This is typically what you will get from a CFME, and it usually runs to an average that you take. If you look at the different limitations and different target values for this particular device, the top blue line, the dashed line, is the design level. That's typically what you will want to have on a new constructed runway. Then you have the maintenance level. That's a trigger when you are below that you have to take maintenance action. That could be removing of rubber deposits or what else. And then you have the level, which is the minimum friction level. If you are below that, you can declare you should declare the runway slippery wet. Now we also have the wheel braking performance of the aircraft involved in this particular overrun, and it's related here also to the position, so not to the speed. So what you see here is the red line is the computed wheel braking friction coefficient for this particular aircraft, and the runway in this example was grooved. You also see a dashed line being drawn. That is based on CSR 25109, in this case section D for a grooved runway. So this is the runway condition code 5, and this is what the aircraft actually achieved in this example. Now, when you look at the CFME does not trigger any alarm that the runway might be deficient, whereas the aircraft is underperforming based what it should have had on a grooved runway. Now, in this particular example, if I remember it correctly, the operator did not take any credit for a grooved runway. So their actual braking performance that they assumed for the performance calculation was a bit lower. But still, this is if you would go the grooved runway way here, this is the difference that you see, and this is very typical with some of the issues that we see with the CFME. So what causes slippery wet runways? We already discussed this a little bit. We think that in most of the cases that, and especially when you look at overruns and veer-offs, that you see that a smooth micro texture surface is responsible. And the micro texture becomes smooth because of normal wear. Using the runway will wear that particular characteristics of the surface. There can be rubber buildup. Most of you will know the rubber buildup at the touchdown zone, which is very visible. But rubber builds also up along the runway, which is not always very visible, but still can affect the runway microtexture, and which is not picked up by the CFME. And finally, that is a bit of an exotic one, but it has resulted in a few accidents, is the use of fog seal and rejuvenators to repair the runway surface. And if they are not used in the proper way, it can reduce the microtexture. And it's a repair thing that extends the life of a runway surface. So it is not uncommon to use. So how to assess runway microtexture? So we've seen in this introduction that we are looking at runway microtexture as a missing link in the assessment of runways, in particular runways that we believe could be slippery wet. The approach taken in the project is looking at the use of a laser scanner, surface laser scanner that scans the surface at high resolution. Now, the use of surface laser scanners is definitely not new. It's been used also to scan and assess surfaces, road surfaces and runway surfaces for macro texture characteristics. And the high resolution part was already known, but it was very difficult in the commercial application. As this progressed and scanners became available in the market that could do a much better job at a much higher resolution, interest was already drawn in assessing runway or road surfaces in particular for the microtexture surface. So this was actually a trigger to look and see, can we use the same principle to assess runways. This kind of approach is also used in the Formula One racing area. And so in that respect, it's not new, but it's the relation in use of runway surfaces. That is particularly new. The device that we use is that it scans an area, a fixed area. It's a static system. It doesn't move. You have to position it. And it's actually scan lines that form the area. So it makes several scan lines of the surface. The approach that we took is actually very simple. So what we did, we used the scanner on several runways, but also surfaces that could be similar to a runway surface. We got the surface scans from there. We looked at algorithms to analyze the particular data, because the data comes in several shapes that are not readily giving us information on the microtexture. So we had to look at particular algorithms that could process the data to get something meaningful out of it, which we refer to as a micro texture parameter, a parameter that characterizes the microtexture characteristics, and to define a threshold. So below this parameter, a certain value, you would declare the runway slippery wet. That's very similar to the CFME approach, where you do your measurements and you have a minimum value where you say, okay, now we declare the runway slippery wet. So the approach in that is similar, but using a different technology. We had several tasks in this project. Typically, we started with a literature survey, looking at the state of the art, what is known, and as I said, you know, a lot of basic work was already done in the road assessments of the friction assessments of roads, and that helped us as a starting point in our project. We did a lot of testing in this particular project, and the testing was needed to gather data for our analysis. Basically, the testing can be distributed in two separate parts. We did flight testing on artificially wetted runways. I'll come back to that later. And we did several surface tests, not only using the laser scanner, but also other devices to determine the characteristics of that surface. We spent a lot of time in looking what algorithms would be best to deduce the microtexture parameters from the surface scans. And there are different approaches. We looked also in the past what happened there, but it was also limited sometimes by the computing power that was available back at that time. We spent time on how to develop a threshold which is meaningful and useful and can be applied. And finally, we worked on the guidance material, how to work with this. What is the practicalities of this? Testing activities. So I'll briefly summarize what the type of testing activities that we have done. As I said, we did flight tests, and I will come back to which aircraft we used. And the main objective was to collect wheel braking friction data on different runway surfaces. It says surveys, but it needs to be surfaces. What we did is a typical classical approach. It's not wait until Mother Nature made the runway wet or a particular section, but we artificially wetted sections of a runway so that we would be in control also of the water depths that were there. As I said, the surface test, we used the laser scanner on a variety of surfaces, not only on those surfaces that we actually tested the aircraft on, but also on other surfaces to collect a broader data set. And we used what is called the British pendulum tester on the same surfaces as on what we tested the scanner on. And the British pendulum tester is typically seen as indicative for the micro texture characteristics. So for us, it was a device that we could use to generate additional data that we needed, except from the as part of from the flight test data. So the flight test aircraft, we had 2 aircraft being used in this project. We had a Citation 550 business jet and a Falcon 2000. The Citation is run by NLR, and the Falcon was by DLR. It's only one letter, but it's our German friends, research partners, which was part of this project too. Both of these aircraft were fully instrumented, so it's not a normal type of instrumentation that you have. It's dedicated, highly dedicated sensors that being installed and used to analyze the data. Of all these aircraft, we also had knowledge of the aerodynamics, the thrust characteristics, and so forth to do our analysis with. Here's an example of a test scheme that we did. As you can see, there's a water truck there. We used a lot of water to artificially wet a part of the runway, and this is not a runway, but we're going to test on a taxiway in this case. You can see the test aircraft being ready there. It's not landing. We did sort of accelerated stop kind of analysis and testing here. And to the right, if you have very good vision, you can see the Citation taxiing back after its test run. A lot of pictures were made, a lot of videos. Don't worry, there was nobody here. Actually, that's a still from a video that was recorded. These are typically the runs that we had done. I also have some live images, a short video. Let's see how it looks. So this is the run of a Falcon 2000. So there's only a part of the runway being wetted. This is a high-speed run. We went up to 120, 130 knots, and full braking is applied in the wetted section. So all the runs are very similar in this respect. So the surface test, we did measurements using the British pendulum and the high resolution surface scanner. So they were on the same section, so it should be similar in that. We did testing on all the locations that we used for the actual flight testing, but we also did, as I said, additional surfaces, including taxiways, road surfaces that could be representative for a runway surface, surfaces with rubber deposit areas, fog spray surfaces, and also very smooth surfaces. Some of them are not what you would see in real life. We also tested on, for instance, on metal plates, just to collect data from a very broad perspective, from very smooth to very rough, sharp. And as I said, the British pendulum tests were used to get additional data used for correlation and validation. So for those who have never seen a British pendulum tester, on the top you will find an example of the device that we use, and also seeing the laser scanner. They're not very big. If you compare both, the laser scanner is very simple. It's got 2 buttons, on, off, and scan, which usually works for everybody. The British pendulum tester is a much more complicated device, which requires detailed calibration, carefully calibration, and can be sensitive to wind and other factors. So you have to be very careful on how to use this device. It will always generate numbers, no matter what you do, but if it's the correct number, you have to be very certain in what you do with this device. So we were very keen on setting up this device correctly in terms of its calibration, etc. So micro texture characterization. So we have all this test data, and how do we deduce the micro texture characterization from this? So from the friction measurements, the British pendulum test, and the laser surface scales. The micro texture can be representation, can be represented by about what SU has developed in a certain model. And that model assumes that you can simplify the texture by using protrusions which are triangular in shape with the vertex upward, shown in here. So these are little sharp pointed elements. So that's a simplification of the microtexture, which in itself can be very sharp, but different in shape. But this is a simplification of it. And what SU did is they looked and say, well, is there a microtexture parameter that is related to the angle of the vertex, F1 in this case? It's nothing to do with Formula 1. So F1 is the angle of the vertex, and you can assume if this angle shown here is very small, you get a very pointy, sharp microtexture, and if it becomes large, it becomes smoother. So the pointiness goes up, down. So on a nearly completely sharp surface, you will go to an F1 of 0, and on a perfectly smooth surface, you go to pi in this case. And this factor, this F1 factor, is the microtexture sharpness factor, which we will call the Boltwell parameter, after Ken Boltwell, who came up with this approach in this parameter. So here's an example how this works. So these are not tests done by us, but they can be found in the literature. And what they did is they pushed a metal cone with different angles into a rubber block and measured the contact pressures at the contact area. And what you see, this is an example of how this works. On the vertical axis is the contact pressure, and the horizontal axis is the vertex angle. And as the vertex angle reduces, you get higher contact pressures. So basically, you get a sharper microtexture from right to left. So this is, the basic concept of this approach. We also use other. We use SU models. There have been SU models being developed, and SU is our partner, one of our partners in this project, and they relate to the microtexture sharpness parameter, the Boltwell parameter. So as I said, the vertex angle determines the contact pressure between the surface and the tire. And a high contact pressure, and that's the reason why we were looking at this, is needed to reduce viscous hydroplaning. So the reason to have a sharp microtexture is to reduce the viscous hydroplaning, to actually regain contact between the surface and the tire when it's separated by a layer of water. So SU has developed models that can be used to derive F1, so the microtexture characteristics from the British pendulum test, but also from wheel braking friction test data. And we use those models in our analysis. The models are basically semi-empirical in nature and have helped us to derive parameters from the data that we have collected, the test data. On the other end, we have the laser scanner, which is also measuring something, and we try to get microtexture parameters from that. That's our basic approach and device that we foresee to be used. So you can, different parameters can be used from the surface laser scans that could characterize the microtexture, and we defined a lot of these based on what we found in the literature, but also what we developed ourselves. And the idea is that you identify that parameter that gives the best correlation with the microtexture sharpness as derived from the flight test and the British pendulum test. So that's the approach that we took. We try to correlate both. Here's an example of the surface scan. This is a single line scan, and you can define as many lines to be scanned as possible. And what you see is the height profile as function of the distance along the line. And on the horizontal axis, the unit is millimeters. What you see is the raw scan profile in this case, and then you have to separate it in the macro texture and the micro texture. So the macro texture, if you do some filtering, clever techniques, this will be the macro texture, the individual stones of this particular surface. This is then the micro texture that's on top. So if you add those, you will get the top picture. There can also be noise. I've not shown this, but there can also be a noise that within the signal, and you have to get rid of that too. But it's the last line which characterizes the microtexture. That's the one that we have been using for our analysis that we have derived from the laser scan. So the correlation analysis, well, it's basically very simple. So we have test aircraft and British pendulum data from which we have derived. It looks very simple, but it's pretty much a very complex process. But we derive values of the microtexture sharpness for different surfaces, different runways. We did scans with the laser scanner where we derived different microtexture characteristics. And what we try to do is find the best correlation between both. And why won't we what's the reason behind this? Well, we want to find the microtexture characteristic from the surface laser scanner that best represents the characteristics of that surface. So here's an example of some actual data that we processed. And in this example is the microtexture height. It was a very simple parameter. And if you look at, closer, so on the horizontal axis, that's the microtexture parameter that came from the laser scanner. And it's correlated to the microtexture sharpness F1. And this is an example. We have many more of these. So that's the analysis of the test data and trying to get something from the laser scanner that is meaningful in terms of the microtexture. But then, we have this data, and where do we draw the line on which we say, okay, now the runway is becoming problematic in terms of its microtexture characteristics. So we need to define a threshold that defines slippery wet runways. What we did is we looked at what is being done in history, and Arman Norheim has been very helpful in identifying a study done by an ICAO working group in 1991. They were looking closely at what they considered slippery wet runway. And what they said is that it's a wet runway on which you have twice the dry brake stopping distance to stop the aircraft. And that's without thrust reversals. So there could be aerodynamic braking in it, but it is mainly the tire wheel braking that is stopping the aircraft. That should correspond to the minimum friction level as defined for the CFME. That was their intention. Actually, if you look back and go back to where this factor 2 of the stopping distance ratio comes from, was based on research done in the US, coordinated by FAA, NASA, and the US Air Force. And that started in the late 60s and run very long. But the main source was those data being generated in that basic research program. The actual study, the US study, if you go back to that, they actually proposed a stopping distance ratio in the order of 2 to 2.5 as the threshold of something becoming more slippery than a normal wet runway break. Now, the whole reasoning behind this is a bit complex and interesting, but it's not extremely scientific, I would say. And if you look back to it, you understand why they did it, and it's something that people, assumed as being a correct way of looking at the levels. So this is what they came up with. What we also looked at is how this relates, this stopping distance ratio between wet and dry, to the current braking friction coefficient being used for a runway condition code of 3. And what we did is we looked at a number of performance manuals, which actually had incorporated the new way of assessing runway conditions, and see how the ratio would be. And it's not entirely correct because there are assumptions made about the braking on a dry runway, which is not fully utilized. We did account for the airborne distance, so we only looked at the stopping distance. And on average, we found that, looking at that, it's medium versus dry, you could get a stopping distance ratio of 2.3. So that's not far off from what they already assumed a way back based on a completely different type of analysis. This actual value can vary quite a bit depending on the weight of the aircraft, even on the type of aircraft and the aircraft manufacturer, based on the underlying assumptions that they have made. But on average, it seems that it's not too bad. So what we use is say, okay, for initially, it's under discussion, is that a slippery wet runway is a runway where you have a stopping distance ratio in the order of 2 to 2.5. So that's where we are looking for as a threshold. So we relate this to braking performance of aircraft as much as practically possible. So how did we come up to this? So what we did is we simulated landing stopping performance for a whole range of aircraft type for which we had appropriate data in terms of aerodynamics, idle thrust, and other characteristics. And what we did is we simulated the stopping distance ratio as function of the micro texture shown. So what we did, we used the SDU models for wheel braking and varied the F1 and calculated the stopping distance ratio. And we did this for a whole bunch of scenarios, different weights, and different runway wetnesses. So the single lines shown here is actually a whole group of lines forming an average. What we then say, okay, we go to look at that area where the stopping distance ratio is either 2 to 2.5, and we look and see what the average F1, so the microtexture sharpness value, would be. We then would go back to our original correlation, which showed in the beginning, is the microtexture characteristic that was derived from the laser cam versus the F1 that we had. And if you have an F1, you can go back to the slide and connect both, and you come up with a threshold for what the parameter that you have chosen as derived from the surface scans using the laser scan. That should correspond somehow to a stopping distance ratio of 2 to 2.5. Now the lines here, you know, they look perfectly, but in reality, they're scattered around these lines, which is very normal, very common. The level that you find for F1, you find different ranges depending on the assumptions, were also matched and validated using estimated values of F1 from landing over accident. So where we know that the runway was really deficient, we try to validate the value that we have found, just to get a sense of feeling. All this has been documented in one of the deliverables that will be published on the EASA project website, with lots more details than I can discuss right now. So the threshold, as I said, you know, we have a proposed threshold, and it's based on a combination of simulations of landing performance by varying the micro texture characteristics. Also, the macro texture levels were varied, and the water depth, which gives us new speed relations based on the SU models that we fed into the simulation. And we had the F1 as deduced from the overrun accidents to give us a feeling of the order of magnitude, if that seems realistic or not. We do say, you know, whatever we have come up with, some further validation is recommended of, you know, what we define as a slippery, what we identify as a slippery wet runway. For instance, by correlating it on the onboard measurements that I mentioned in the beginning. That helps to identify runways in Europe, for instance, or parts of the runway that from the assessment of the onboard measurements would fit a runway condition code 3, where the wetness is not, you know, such as it being flooded or very significant. That can help to further validate what we have developed here. So we're coming to the end, the findings and next steps. So we have a new method based on developments that were already ongoing, but then we looked at using it for a runway. That gives us an objective assessment of the runway micro texture. And people can say, well, CFME is also objective. It is, but it has shown deficiencies in assessing whether a runway is actually deficient or not. And as I said, you know, it can help us to assess the braking characteristics in a more consistent way, and which is much less subjective in an easy way. Although we see all these complex things, the idea is that things will be automated and that a laser scanner, surface scanner, will already do the computation for the user, whereas the user doesn't have to do all the details. It just gets an answer from the device directly. And as I said, the method aims to help in determining slippery wet runways. Now, you can also say, well, what about maintenance level and design level, which we have currently for the CFMEs. The whole scope and objective of this project was not to look at that particular area. So that could be something that could be considered later, but it's not being considered here. We only looked at the threshold that defines a slippery wet runway, as that is also part of the current runway condition assessment matrix used by. So next steps, and Vasilius will also come to some of those. So we still have to make choices which texture parameter that we derived from the surface laser surface scans we should use. There are several ones, some advantages, others. Yeah, we should, you know, look at how the threshold would establish on a very common basic accepted criteria, which not necessarily only have to look at the micro texture, but also a very smooth macro texture surface can also result in a slippery a wet runway. So you have to also look at that combination too in the operational practice. Other devices, we initially looked at optical devices, but decided not to continue with that. Optical devices are also used to scan surfaces, and these can be portable now. There are portable devices available, and they work different from the laser scanner. They actually make a complete surface scan based on microscopic principles. And again, they are used in the Formula One racing scheme to assess the racing track surface conditions. And again, as I said, you know, the approach needs further validation. And for that, we can use it by, for instance, airport operators and accident investigation. My final slide, there are always open issues, and there are things that makes, you know, runway friction complex. One of the things is water depth and operational measurements of water depths. And that's particularly related to the aerodromes and how to use that. Maybe, you know, the surface temperature, I briefly mentioned it. It's something that we considered in the analysis, but its role in wet runway friction is not fully used. You know, if you have this, you know, you have a wet runway in Asia where it can be very hot, or a wet runway in Amsterdam where it can be very cold. Is there a difference, and how big is that difference? Macro texture depth, although we looked at micro texture, say macro texture depth, macro texture is solved. At least in Europe, we don't have real minimum values. ICAO doesn't either have minimum values where you say that now things needs to be handled. I know that the FAA does, and I think, you know, we believe that minimum values also need to be established for macro texture depths. Now, this all needs to be in an integrated overall review. You know, how does it relate to the operation, airworthiness? It all relates to safety in this. And finally, you know, you could say, do we need to review or revise the runway condition code underlying assumptions? So basic risk condition matrix, it lumps things together. Are those levels still valid? Do we need to change that? So this is a question mark. So it's something that that you should keep in mind for any future activities. So this is in brief, although with a lot of technical content, the work that we have been doing in the last 3 years, and 50 slides does not really justify all the work that's being done and all the details that are related to this. And as I said, on the project website of EASA, the public documents related to the results will be published. Okay, that's it.
So then, thank you very much for this great presentation of the project results. Actually, it was more than a presentation because you also made a lecture.
Sorry about that.
What are the, no, this was really great. Huh? What are the basics of wheel braking? What are the definitions? How do you do the testing and so on? It was really great. Thank you so much. And I just want to say, I mean, what you present here is a whole team behind you who were involved there. So you have done really a really great job. So we have here, I would say, very good project results. It's important for us, of course, that we do not stop here. So we do a research project in order actually to achieve something. So basically the real work will come now. And I would like to ask my colleague Vasilis, who basically will be now in charge of following this up? What kind of next steps you plan? Please, Vasilis.
Yes. So, as correctly said, really now our job starts.
Yeah.
And as you see, there are quite a number of proposals, what needs to be done. And also there are some open issues that also needs to be discussed, assessed with experts. And of course, the outcome of this work is, well, as we said at the beginning, is to increase safety. In generally speaking, we have in mind that we will initiate a rule making. So does not really necessarily mean that we are going to change rules, but we need to first of all to think how to establish these microtection values. So we need to take the report, we need to check the results, we need to decide what will be the microtexture values below which a runway would be considered a slippery wet. And the microtexture well assessment is part of the overall assessment because it's not only the microtexture that plays an important role on the condition of the runway surface. It's also the macrotexture. It's also the visual observation that you are using. So it's not only these tools, but also sometimes you have to go and see your runway. I think the forward circular 355 of ICAO at the end, it explains in a very nice way, in a simple way, what is the overall assessment. So all these things need to be considered. And of course, this has to be given to the aerodrome operators as a tool. So what we are thinking is to develop a guidance on the method that will be used to measure the microtexture. So we envisage that there will be some how to do instructions. I cannot tell for the time being what will be the details, but the important is that we provide this information, an information which is going to be usable for them. Another thing is, it is also in line with the work at ICAO that we need to establish clear criteria for the development of a trend monitoring program. So how you measure your runway surface, microtexture, and when you consider that maintenance actions are necessary. Then we need also to review the certification specifications regarding runway surface construction. I think this is a more complicated task, but at some point we need to look into this issue. And finally, we don't want this work to remain within the EU, but we want to make it global use. And we think that the best way is to present the outcome of this work to ICAO. They have the friction task force, for example, and the aerodrome airfield pavement expert group, where we can present and provide more details and see how we can include this method into the ICAO documentation, namely the Airport Services Manual Part 2. Of course, it will not happen overnight, but we consider that we will start work well in some months from now, and then we think that in a time period of 2 to 3 years, maybe we will be able to have some concrete results. I think that's it from our side for the time being, and then now we are ready to receive questions and provide answers if we are able to do so on the spot. So
thank you, Vasilis. Then let me perhaps take over the screen. So colleagues, you see here once more the QR code for the Slido tool. So we kindly ask you to use this tool. What you can see here is there's some questions who have been actually ranked or actually voted also by other colleagues. These are the ones who come first. And then I would say we take the sequence that we start actually with the oldest questions, and then we go back to the newest one. So if fine for you, colleagues, I will just read out the ones which we select, and you please be so kind and would then answer. So let's start with the first one. What should be a reasonable combination of sharpness of micro texture and tire wear? The greater the sharpness, the greater the tire damage.
That's a good question. Yeah. It's also not an easy one to answer. So there is a relation between the amount of tire wear and the micro texture sharpness. So at some point, if you make it too sharp, and it can be in the extreme case, tires can wear much quicker. So there has to be a balance. Where it actually is, it's difficult to say. No, there has been some research in the past. It's not something that we looked at in particular, but there is not an idea to have the most sharp surface, because then you run out of tires quite quickly. So yes, there is a combination. That's up to also to the experts that construct surfaces, in particular road and runway surfaces. Yeah, that's what we can say. We did not look specifically at what level of microtexture would bring tire damage to a too much higher level in that respect.
Okay, thank you very much. Any colleagues wants to add? Good, then I would say we move on to the next one, which is from René.
Yeah.
Slide 48. I will show the slide 48.
I know what it is. Yeah.
And,
yeah.
Yeah.
Okay.
I don't know, because maybe the other colleagues would like to see it, but I just read it out. For the determination of the SDR of 2.3, is this only based on the FCOM performance table or also the single point landing performance calculation? And here is the slide.
Yeah. So this is only done on the data that we had available, and we did not have the SCAP calculation. So we used the basic FCOMs to get a first impression. What we did do is, because the landing distances provided there, they can have regulatory margins, so we removed that. And we also removed the airborne distances. Either there was a fixed distance given. Some of the manufacturers have a fixed distance, so we could easily correct for that, and others use the approach in terms of a fixed decay of the approach speed from threshold to touchdown, and a time for the airborne distance. But it was for us to get a feeling of the order of magnitude where we would come from there. And as a next step, if you want to validate this further, the aircraft manufacturers could play a more active role to do more detailed assessments. This was to get a first impression. So we only used the performance tables that were in the FCOM or in the quick reference handbook of the particular aircraft that we had. We looked at what we had, and there were business jets in it. There were small regional jets, narrow bodies and wide body aircraft in it. And I wouldn't necessarily say it's representative for everything flying around, but it gives a flavor of where you get and where you go in terms of this number.
Thank you, Garrett. And also Renee just replied, thank you and great, all clear. Thank you, Renee. Then I would say we move on to the next question, which is from an anonymous person, stakeholder. What would you say to an airport that hesitates to use the new methods, lasers and BPD, because it might lead to higher costs if braking performance data is bad?
Yeah.
Good question. Huh?
It's a good question. Yeah, and we've heard that before. You want to?
Well, up to now we were using mainly the CFMEs. We had some reference values, and we all know that in ICAO these reference tables have been removed. We maintain them at EASA. If we found that, we have a new method that provides results which are reliable and they indicate poor performance, and we also have, as Gerard mentioned, there were cases where the friction measurements were showing a good runway performance, but in fact the actual situation was much worse. So if we have this method and it provides reliable results, then you need to maintain your runway. Sometimes it's an additional cost, but at the end of the day, we talk about safety.
Yeah.
So.
And maybe if I can add to that, I really hope also this is a really just a hypothetical question, right? Because I'm sure that aerodrome operators, if they see that the braking performance is bad, they will certainly act. Huh?
Yeah.
I think also the competent authority will make sure that such improvements will be done. So I hope really that this is only a hypothetical question. I'm quite confident.
Yeah, and maybe if I can add also a runway excursion, if it were really to happen.
Yeah.
And we have seen very interesting data that shows that it's almost similar to icy or snowed runways at times, something that we would not assume.
Mm.
So if a runway excursion would happen, and this is a huge cost for the aerodrome, also because it basically stops the aerodrome, especially here in Europe, we don't have 4 runways to choose from. So if your runway is blocked, there's not much that you can do, and your operations are seriously impaired, and it will take a long time to recover. So that's why, of course, it's in the interest of an aerodrome to prevent runway excursions for reasons of safety, but also for reasons of costs.
And I can add to that is what is also a very worrying situation if the pilot thinks that the braking performance that he can achieve on a wet runway is good, and not knowing that the runway might be much worse. So if you as an airport identify this in a proper way, you will inform the pilot with the right information and to the pilots, and I know that there are a couple of pilots in this session that will confirm this. Not knowing is really bad. They have to have the best information in terms of what's out there, and so even if your runway is worse, it's a fact. But not knowing and the pilots not knowing is even a much more serious case. So from that perspective, I look at it from a flight safety point of view.
Yeah. Thank you, colleagues. Anyone wants to add? Then I mark this as answered, and I move on to the next question, which is again from an anonymous participant. How long does a laser measurement of microfriction a whole 4-kilometer runway takes, and how is it performed? Manually mounted on a vehicle?
Yeah.
I think
That's a good question. First of all, depending on, you have a 4-kilometer runway. The device that we are now using it is only capable of doing static measurements, so at selected spots. Because if you want to measure at a very high resolution and you want to move the device, the frequency of the device has to go up, the scanning frequency. I'm not saying that it will come in the market. As for now, it's not yet available. So you have to do static measurements. And that's very similar to the measurements that you would do if you do micro texture assessments using the sand patch or grease patch methods. So you have to select spots at a regular interval. And also in those areas of interest, that is typically where you expect the main gear tires to be present, left and right of the center line, certain distances. The scan itself, it depends on how many lines you scan, and there's the number of lines that we scanned was sufficient for the analysis, so it will also be sufficient for the assessment, and that takes about 2 minutes per scan. Yes, it takes time, but it's not something endless. I do hope that in the future, the laser scanners or maybe the optical devices improve such that you can mount it on a vehicle, and then you can also do similar, like a CFME or a profilometer, do scans along the runway surface much more quicker, and you have a larger volume of information. So for now, the approach will be to look at it at selected spots, similar to what is done for measuring macro texture using sand patch methods.
Thank you, Gert. Any comments? No. Okay, then I mark it as answered. And we move on to the next question here. We are using ASFT equipment. What is the experience of the reliability of it? Not sure if
okay, I understand. Yes. Okay, but okay. First of all, we have to make clear that we do not say that friction measurement devices are not reliable or they provide false information. What we say is that you cannot base your assessment solely on ASF, on friction measurement devices. And I think I saw somewhere in the comments, someone mentioned the EASA rules, where we say that the assessment is a part of different ways. So it's the ASFT, it's the friction device, it's the visual inspection. There are many other things that you need to consider when you are evaluating your runway. So we cannot support this statement that friction devices, measurement devices are not reliable. And well, of course, we are not aerodrome operators and we cannot provide you with our experience, but we cannot support that statement.
Good. Thank you. Anyone wants to add? Then the next one. What do you offer for rubber removal? High pressure machine or liquid material? It's not really the scope of
we cannot say
of our webinar. Would you like? I mean, I think we from an authority don't have.
Promote.
Yeah, it was really it was not part of our website. So I would skip this one then. I hope the person who raised this question will understand this. The next one, I think,
Yeah.
Vasilis, you already
Yes,
also
yes.
answered this here. Airports perform friction measurements on a frequent basis. Yes. Does it mean that these measurements aren't considered reliable?
I think I responded that it's part of the overall process, so you cannot base your assessments only on these devices. You need to consider also other things when you are making the assessment.
Yeah. Okay. So then the next one is actually looking into the follow-up actions. Question to EASA. You mentioned taking action soon, showing results in 3 years. Is that via ICAO or also via EASA rulemaking group in Belgrade?
Well, what I can say for sure is that we are planning to present the outcome in the next, I think, friction task force meeting of ICAO, which is going to be next November. Of course, we will try to work a bit in parallel because there are experts not only from Europe there are from all over the world. It's very good to have synergies. I cannot provide the details now, but for sure it's going to be coordinated work there.
Thank you. The next question is from Patrick from the Swedish Airport Authority. No, Swedish Airport, sorry. A very good question, I think. Does presence of an invisible thin water film on the runway surface influence the effectiveness of micro and macro in maintaining friction and preventing hydroplaning? I think this is will for you.
Well, I'm not sure what invisible is. But if there is a certain level of water, and if we're talking water depth, it's typically the level of water on top of the asperities that we see. So there can be water in between the asperities, in individual stones, and at some point it will not have a major effect on it, especially the macro texture. So it depends also on the amount of macro texture that you have. If you have a good macro texture surface, then the water drains easily, and you will have water also in between the stones, so the effects are less. So there's a combination of that both. But the effectiveness will be the same if you both have good macro and micro texture. And macro texture is particularly important with the higher water depths and drainage of the characteristics, but also to prevent dynamic hydroplaning, so the zone 1, whereas the micro texture is fully on the middle zone of the contact pressure. So it's not easy to answer this, but both play a role. Where if you have a very thin layer of water, the micro texture could be more important. Hopefully, I understood the question completely. And otherwise, Patrick can send me an email or send us an email.
Yeah. Thank you very much. Yeah, colleagues, you can always, of course, send us also emails after this webinar, of course, and we will certainly give you a response in a reasonable time period. Mark, this has answered. Move on to the next one, which I think is also very good. Did the project discover low aquaplaning speeds for wet runways? And if so, did they correlate with microtextural surface conditions as well?
Okay. So typically when people speak about aquaplaning or hydroplaning speeds, they are referring to dynamic hydroplaning, because that's a very distinctive characteristic that we see, is that the tire stops rolling, it spins down, you have less spray, typically with a lot of water. You can easily see this. And that's a speed that we define. When we look at microtexture, and when we're talking about what we call viscous hydroplaning, there is a relation with speed, but it's not like what we have with dynamic hydroplaning. So it continues over a very broad speed range, and can be if the speed increases and you have also dynamic hydroplane, because these things can coexist, then it can take that over. But we have seen on a few very slippery, very low textured micro texture surface that you will see lower values that are attributed to that. But we did not discover low aquaplane speeds in the relations to the classical view of dynamic hydroplaning in that respect.
Thank you. So here is a comment from a colleague from the CA Netherlands, slide 26. I will show the slide.
Yeah.
Are there any research reports on the effect of applying Fox seal regulators on the friction values for macro and micro texture? Please provide the link if this is available. I just go to slide number 26, which was this one here.
Yeah. I don't have the link, but there is material.
Yeah.
And I noticed that it's Harry van Dijk from the Dutch CAA.
Mm-hmm.
So maybe we'll put it on the. We'll see. Maybe we put it in a Q&A document or something.
Either that, yes, and
Yeah.
we could also actually add this to the project.
Yeah,
as
maybe
well
there's
as
there is public information which
Yeah.
which discusses this.
Yeah.
So.
Okay.
By the way, Vasilis, when you move the mouse, you have an effect on the slides.
Oh, yeah, okay, sorry.
Okay.
Oh, sorry.
So thank you. No problem. Let's move on to the next one. How does this concept work for concrete rigid runways?
Yeah. So I think the concept is scanning, I guess. Yes. So there's no difference in if either is you have concrete or flexible or rigid surfaces. So the scanning will be the same. The deduction of F1 accounts for either a flexible or a rigid surface. So that's taken into account into the method that SDU has developed. So those details are considered.
Okay. Thank you. Then we come now to the question you just mentioned, ESDU. So there is now Ken. And we have here, I think,
the third. Yeah.
We have three, so basically the three questions are in one, when I understand this correctly. During the Runway research program, more than 500 measurements of British pendulum readings and simultaneous laser scanner outputs were taken. Preliminary correlation has shown considerable promise, but more analysis is required to have a clear understanding of the relation between braking action and surface characteristics by way of the sharpness parameter. And is such an activity planned for the near future?
I think we will not stop where we are right now. So we're looking at what we have been doing, and I think also as this materializes into like the ICAO friction task force, there could be more interest of additional analysis. And as I said, also that there are some new ways of analyzing the texture characteristics using a technique called wavelets. If you're into mathematics or you have problems sleeping, I would recommend reading about wavelets. It's very complex, but I do not fully understand it, but we have people that understand it, and this is something it's been considered very recently. So yes, that might be a help. To answer this, I think there will be activities in the future.
Good. Then thank you very much, Ken, for these questions, and I will now mark as answered all three of them, and then move on to the next one here. Can you give some examples of a CFME? What different CFMEs are there? Mark.
Yeah, can I? Yeah. Well, so there's a Well, the basic functioning of a CFME is that you either have it integrated into a car, or you have a separate trailer where you have the device mounted. And the basic characteristics is that you have a measuring wheel, a dedicated wheel that has been designed according to certain specifications, and water's being applied in front of this particular tire, and it's braked in a fixed manner. You can have differences there in the way you measure the friction forces on this particular test tire. It can be either aligned with the runway, but the tire can also be at a certain angle, which you have on the mu meter. There are a bunch of these devices out there, and you can typically find them in ICAO documents on this matter. That's what I can say about it.
You want to add something, Vasilis, or?
No, what we can say, we have the CFMEs, were different type of vehicles, but we cannot list them all, and we cannot refer to specific manufacturers.
Yeah.
But there are also other things, the decelerometers, which are another way, but not for maintenance purposes, mainly for operational purposes. So, yeah.
Okay. Good, thank you. Then we come to the next comment or question. Is the test study performed on different types of asphalt surfaces, SMA, asphalt concrete, or anti-skid surface?
Yeah, I can confirm that. So as I said, we did test with the test aircraft, and of course we are limited what we can do. So we tested on actual runways, being made of an SMA or with an anti-skid surface treatment. We also tested on concrete runways of different wear, and we also tested on a taxi concrete runway. Considering the test that we did with the British pendulum tester, the additional test, we went even further also on more extreme surfaces in terms of the characteristics that it had, but it also varied from concrete to asphalt surfaces. So we try to be complete. We also tested on grooved runways. That is particularly challenging. A British pendulum tester on a grooved runway is not easy to drive values from that. The surface scanner, because it scans lines, you have to be careful in the way you set it up, because you don't want to have the scans in between the grooves, because that's not representative of the contact area. But yes, we did test on a variety of surfaces, which are described in the reports that are being published.
Thank you. Can you explain again why rejuvenating measures can negatively impact micro texture? And I go to slides 27.
Yeah, that's the one.
Is the one?
Yes. Yeah.
What this?
No, it wasn't the right one. Yeah, the right.
It was 26 probably.
26, yeah.
Yeah. So what can happen then if you apply these repair techniques, especially if you overdo it in the amount of material that you put on the runway, it can fill up the micro texture basically. So you will actually remove the micro texture of the surface. And there are techniques there with additives to it that will compensate for that. So you have to be very careful on when you do this, that the contractor, the people that do this, know their business. Because you can buy at the hardware store, you can also buy these stuff if you want to repair something on your porch, if you have an asphalt driveway or whatever, and you can put it on and it's nice there, but it's not the same application that you would use on a road or particularly on a runway. And what we have seen in a few cases in the past is that companies were involved that were not very familiar with runways and the criticalities of a runway, and especially when it becomes wet. They were applying the material in too high a volume or not with the proper combination of an aggregate that was added to the material. So that's basically the background in this.
Thank you, Garrett. So we come already maybe to the implementation.
Yeah.
Are those surface laser scanners very expensive?
They're much cheaper than a CFME.
Yeah,
that's the first thing, and you can imagine that because the CFME is usually a big device, could be a complete car. So I don't have the numbers here, but it is typically much cheaper. It's still expensive. It doesn't cost a few €100, dollars, or what units you're using. But it doesn't cost 100,000. You know, it's because it is being used at a certain level in the industry, so it's used at a reasonable high demand for it. So that also raises the price. So yeah, I just make a comparison with a standard CFME. It's a lot cheaper than a CFME. Also, it depends which CFME you're looking at, but typically it would be cheaper.
Thank you. So is the laser scanner used widely today in airports? I assume you said they are mainly used in Formula One, but not in aviation today. How can we use them?
Well, the type of laser scanner that we have been using is a high resolution one. It's not really used at airports. Airports can use and contractors that help airports in resurfacing use surface laser scanners, but these are the low resolution one that look at macro texture only. So those are used and also on road surfaces. And yes, Formula One is always ahead of things. And so they have already discovered the value of using this. They keep it quite secretly what they do with it. They asked us for some information, but it's not like that they share what they do with it. But it also shows that, you know, it's something, a technology that is used to assess these kinds of things. And how can we use them? Yeah, that's part of the project and the next steps. That's to define how we should use them, because Formula One is different from an aircraft. Although the mechanics can be the same, we have different things that we look at. So,
thank you. Next question. From the 5 open issues on slide 54, which one is the easiest to do next? So we are on this slide here.
Yeah, the macro texture depth.
Yeah, the macro texture depth. Yeah. That because
there is work.
There's already work there, and you know, so and it has to be related also maybe with the micro texture, but that would be the easiest one. Yeah. Yeah, and it's something that I would recommend also because FAA does have details on it, and I haven't seen.
No. I don't think that someone else does.
No.
I know FAA they have.
Yeah. But that would be the low-hanging fruit. I'm not sure if I can call it that way, but it's there.
Good, thank you. So when we act with the values in the ICAO tables 3.1, if we see a value below 0.5, grip tester, we start maintenance planning. Is this the right approach?
Okay, okay. So my response to this is that, well, I don't know if it's an airport asking this question, and if it's an EQ airport or airport outside. Well, the ICAO, I think the 3.1 does not exist anymore, has been deleted from ICAO, and you can, it was available in Airport Service Manual Part 2. I'm not sure if you will find it in the next edition of the document, because the document is under very significant revision. At least for Europe, we are still using this table as a reference. I will not say that if you start maintenance planning is the wrong approach. So if you want to do it, you can do it. But as I said before, the assessment is the outcome of a holistic approach. So it's not only the CFMEs and that play a crucial role to dictate your maintenance program. But of course, you have to consider.
Thank you. Then I think, Vasilis, the next one is also for you. Is EASA planning to include surface laser scanners in the safety-related ADR equipment to be certified?
Well, I cannot tell this now, because I think these surface laser scanners are commercially available. It's not that I'm not 100% sure, but this is going to be, well, if we decide to do so, we will take the decision at a later stage, not now. Because if it's something which is commercially available and used for also for other things, I don't think that we need to certify, but this is something that we cannot say now.
Yeah. And I would assume you need specifications first for this equipment, right? And I'm not sure
we need to check different things, yes.
Good. Then we have 3 remaining questions, and they all are from Kevin. Yeah. So the first one: what distribution, number and spacing density of static micro and macro texture sample size is adequate, is optimal?
So yeah, and I it also relates a bit to the second question of Kevin, but I first the first one. We have addressed that and will address that also in some of the guidance material. And there is actually, I think in the ISO standards, there is some guidance already on micro texture sample spots. And it also depends a little bit on the what you actually witness seeing on the runway. If the runway is very consistent in the construction, then the number of samples could be less. If you see different material being used, then you have to make different tests. So if one part is made of concrete, one of asphalt, you have to, of course, make several samples. I think we look at every 100 meters, left and right. And coming back also to your second question and a little bit, the wheel path travel area is important to make samples there. The pavement condition I already mentioned. Yeah, if you see that the pavement condition is changing, you can really witness it. Coloring, that might also be a trigger to make more measurements, spot measurements. Ideally, we would like to have a continuous measurement, but this is not yet practical. But I don't, I'm hopeful that if this gets more attention also from the manufacturers of this type of hardware, they will look at ways of increasing the frequency of the measurement, so that you can doing a measurement based on a device that is built on a vehicle that runs along certain paths. But for now, it's not there yet. So I think it's also question 2.
Yeah. then thank you very much. I will also so we have a last question also from Kevin. What practical methods short of payment replacement exist to improve runway micro texture?
I know there are some techniques, but I'm not a specialist on this. There are techniques, and I'm not saying that they all will work. And at some point, a runway is just worn out, and you cannot do anything, then resurface it. So from my point of view, I can't really answer this.
But I think this could be also a very good follow-up action, actually, to check that.
Yeah.
Good. Colleagues, are there any questions maybe from the audience here? That was our last question, colleagues. Then thank you very much. I move back to our slides. I will continue if this is fine for you. So colleagues, we were basically here. We have done this. We come to the concluding remarks, colleagues. The concluding remarks are, first of all, thank you so much for all colleagues who attended this webinar. I hope you found this very interesting. I certainly did. I would like to thank very, very much, in particular, Garrett and Vasilis for your presentations, as well as for providing the answers. I would in particular like also to express my great appreciations of NLR and all the team behind that. We have done a very, very good job. Thank you very much for that. I think this was really, the money we invested here, the EU money, was very, very well invested. Many thanks to Vasilis and his team, and also Giovanni, Julia, of course, for guiding this project on the technical side also at EASA. I think this also contributed to the success of this project. Colleagues, we will upload the presentation as well as the recorded webinar on the events page as well as on the project page of EASA. You see here on the last slide actually the link to the, well, you don't see the link here, but when it's uploaded, you have the link in order to see more about the project website, where you find also then the public deliverables, which are a lot of them. Not all of them are yet published, so there will be, I think, 3 more public deliverables which will be uploaded in the next 2 to 3 weeks, I would say. And yeah, and with that, colleagues, if there are no further items, I would like to close this webinar. Once more, many thanks, and have a very good rest of this day. Bye-bye.